Hello everyone and welcome to my video on integration by substitution, and we'll throw in a little numerical integration as well, which is 4.6. The objectives for this video are: number one, use pattern recognition to find an indefinite integral. Number two, use a change of variable to find an indefinite integral. Third one is use the general power rule for integration to find an indefinite integral. Number four, use a change of variable to evaluate a definite integral. Number five, evaluate a definite integral involving an even or odd function. And number six, approximate a definite integral using the trapezoid rule. What I'd like you to do in terms of starting out here is I just want you to recall the chain rule. And the idea with the chain rule is that we had a function y, which is going to be our outside function, f of u, and our inside function was g of x. So if I wanted to take the derivative, find dy dx, if I want to take the derivative of that, I'm really looking at taking the derivative of f of g of x. And when I did that, I took that was going to be f prime of g of x times g prime of x. In other words, I took the derivative of the outside function with respect to the inside function times the derivative of that inside function. And then because of that, because this is the derivative of that, I know that if I was to go and take the integral of f prime of g of x times g prime of x dx, the result would be, because I'm finding an antiderivative, would be f of g of x plus c. That is what we're going to be working with today. We're going to be dealing with functions that are written in this form right here, and we want to be able to find that antiderivative. So what we have is a theorem here. It says let g of x be a function whose range is in the interval I. If g is differentiable on its domain, and if f is an antiderivative of little f, if capital F is an antiderivative of little f, then the integral of little f of g of x times g prime of x dx is going to be equal to the capital F of g of x plus c. Now if we let u equal g of x, we can go through, find the differential of u, so du would be g prime of x dx, and therefore this integral up here could be written as the integral of f of u du, and it's going to equal capital F of u plus c. Now as we go through and do these problems, there's going to be a couple different ways we're going to use this idea of a u substitution. The first one that we're going to talk about is what's called pattern recognition. And this is really where you recognize the pattern that we see, that f of g of x times g prime of x in the problem. And often this is going to be performed mentally. You're not necessarily going to go and actually physically write things out. And I'm going to tell you right now that while I see most of us ending up doing pattern recognition quite a bit, it is not going to be something that's very common initially. Okay, it's going to be helpful to actually physically make the change of variable. And that's the other one. With the change of variable, we identify what the substitution is, identify du, and we completely rewrite the integral in terms of u and du. So when I look at the problem, I'm not going to see an x anywhere if I'm doing a change of variable. Let's look at one here that would be a pattern recognition problem, at least to start out with here. What I have is the integral of the quantity x cubed minus 4 to the 6th times 3x squared dx. Now I look at that and I see the x cubed minus 4, that is inside. I look at that, so I'm going to say, I'm going to let g of x equal the x cubed minus 4. Then when I take the derivative, I get g prime x equals 3x squared. So when I look at that, I can say, oh, this part right there, this is my f of g of x. This is my g prime of x. And so I recognize the pattern that we have. So when I look at that, this really is then a power rule. It's just a general power rule. I'm integrating this. My little f is something to the 6th power. So if I want to integrate something to the 6th, I know I'm going to get 1/7 times that something to the 7th. So I know that this integral here is going to become 1/7 times x cubed minus 4 to the 7th power plus c. The way you can check this is, and I'd like you to do this right now, take the derivative of 1/7 times x cubed minus 4 to the 7th and show that you get this expression, the x cubed minus 4, that quantity is 6 times 3x squared. Take that, show that you get it, and then we'll move on to the next problem. Now here's another one that is that we're going to use with pattern recognition. I look at that and I notice in here that I have a 2x to the 4th plus 3, and I have an x cubed out there. So I'm looking at a pattern recognition. My problem is when I identified g of x, I said g of x is 2x to the 4th plus 3, and g prime of x is 8x cubed. Well, in this case, I don't have the 8. Well, what I can do is I can go through and multiply, in essence, by a fancy form of 1. And that fancy form of 1 is going to be this. I'm going to take this as the integral of 1/8 times 8 times the x cubed times the square root of 2x to the 4th plus 3 dx. Now in this case now, that 1/8, this 1/8, I'm going to pull that out. So that's going to be 1/8 times the integral of 8x cubed times the square root of 2x to the 4th plus 3 dx. Now, at this point, what I recognize on this is that now we recognize that pattern that we had. And I look at this one, I notice my outside function is just really to the square root, which I can think of that as 1/8 times the integral of 8x cubed times 2x to the 4th plus 3 to the 1/2 power dx. And so by using the general power rule again, I know that this one is going to become 1/8 times 2/3 times the 2x to the 4th plus 3 to the 3/2 power plus c. Or, when I simplify that, I'm going to get 1/12 times 2x to the 4th plus 3 to the 3/2 power plus c. Check this again. Take the derivative of this expression to show that you get back to what we had up here. The next type of problem we have is what's called a change of variable. And this is actually where I see most of us going to start out with here, and then gradually moving more into the pattern recognition. In this case, what I want to do is I want to integrate x squared times 6 minus x cubed to the 5th power dx. So what I'm going to do on this one is I recognize my inside function is the 6 minus x cubed. So I'm going to let du equal 6 minus x cubed. I take the derivative of that, I get du is going to be negative 3x squared dx when I find that differential of u. And realizing that this one has an x squared and a dx doesn't have the negative 3 with it, I could say x squared dx is du over negative 3. So I went through on this one here. I moved things around. I put the x squared over with the dx. And so when I look at that, I say that this part right here, that is u. That's du over negative 3. So when I make that substitution, I get the integral of u to the 5th times du over negative 3. Now, one thing I can do is I can pull the negative, the negative 3 down here, which is actually negative 1/3. Pull the negative 1/3 out times the integral of u to the 5th du, which is just a power rule. So I get negative 1/3 times 1/6 u to the 6th plus c. Multiplying that, that's going to be negative 1/18 u to the 6 plus c. But remembering that we always need to go back to x, u is 6 minus x cubed, so this is going to be negative 1/8 times 6 minus x cubed to the 6th power plus c. What I want you to do right now is pause the video, make sure you're comfortable with each step that I did on this one. If you have any questions, make sure you ask them in class next time. We will also do a couple more examples of this as well. But pause this video, make sure you're totally comfortable with where we're at right now. Let's take a look at another problem. In this case, what I have is the integral of the sine of 4x raised to the third power times cosine of 4x dx. In this case, it's a little bit trickier on this one, but I look at this, I'm going to say, well, u is the function that's inside the parentheses here. So I get u is sine of 4x. Du then is going to be the derivative, the differential for that, which is going to be the derivative of sine of 4x, which is going to be cosine of 4x, times the 4, times the derivative of that inside function, dx. And again, realizing that I don't have the 4 there, I can go and divide through, so I get du over 4 equals cosine of 4x dx. And at this point now, I can make the substitution. I know that this part right here, that's u, and that part, this part, actually goes all the way over, is du over 4. So when I make that substitution now, I have this portion has become the integral of u cubed times this part is replaced by du over 4. When I pull the 1/4 out, I get 1/4 times the integral of u cubed du. And again, we're undoing the power rule with this, so we have 1/4 times 1/4 u to the 4th plus c. So I get 1/16 times sine of 4x to the 4th power plus c. That would be my antiderivative. Again, at this point, I'd like you to pause the video, make sure you're comfortable with each calculation I did on this problem, and then once you feel comfortable, we'll move on. Or also make sure that if you're not comfortable, if there's something you're not sure about, remember to make a note of that in your notes and ask about that in class. Here's our next problem. We want to do this one we're going to take the integral of x cubed over the square root of 1 plus x to the 4th. And what I want you to do is I want you to find u and du. And I'd like you to make the substitution in there and then see what you can do with getting that indefinite integral. So pause the video, find u and du, make your substitution, and then integrate that and see what you get, and then come back and we'll go through it together. Okay, welcome back. In terms of this problem, u in this case, you should have used 1 plus x to the 4th. Du should be 4x cubed dx, and therefore du over 4 would be x cubed dx. And I will do that because of the fact that in this problem, I have the x cubed dx, I don't have the 4. So I got that 4 over on the other side. So when I do this now, this thing with now doing the substitution, this is going to become the integral of 1 over the square root of u times du over 4. Or I will get 1/4 times the integral of u to the negative 1/2 du. So now integrating u to the negative 1/2, when you did that, you should have had 1/4 times 2u to the 1/2 power plus c, or I'll get 1/2 times 1 plus x to the 4th to the 1/2 power plus c, or if you wanted, you could just say that is equal to 1/2 times the square root of 1 plus x to the 4th plus c. So that's what you should have come up with when you did this problem. So double check, make sure if you didn't get this, take a look at what I did, make sure you had the correct choice for u and du in this case. If you have something different for you and you want to know why that wouldn't work, please, again, make sure to ask about it in class. Hopefully everybody did this one the way I did it, and everybody's feeling comfortable. So let's go ahead and let's move on. You are going to see some problems where they tell you to do something like example 5. So what I did here is an example 5 type of problem. And what we have, the idea behind this one is that when I make my inside function, if I was to go and take the derivative, I wouldn't be able to do a complete substitution as it was written. So like what happens here in this one, we're going to go through and identify what u is, and then we end up solving for x, so that we get, so instead of going through and taking the derivative of u first, we will go and get, we have u equals something, then we'll say come up with x equal to something, and then we'll go from that point on. So in this case, what I have is I have the integral of x plus 1 times the square root of 2 minus x dx. So what I'm going to do on this one is I'm going to let u equal that, what's inside there, the 2 minus x. So taking that and solving it for x, I'll add x to both sides and subtract u. I get x equals 2 minus u. And then taking the derivative, dx, is going to be equal to the derivative of this side, which is going to be negative du. And now what I do is just make the substitution. I'm going to replace this x right here with the 2 minus u, and I'll replace the 2 minus x with u, and I'll replace dx with negative du. So in this way, I've now gotten rid of all the x's. I'm just looking at a function of u. So that negative sign there, I just pulled that out and brought it out here. That's going to be negative integral of, when I combine the like terms, I'll get 3 minus u times u to the 1/2 du. I distribute that u to the 1/2, so I get negative integral of 3u to the 1/2 minus u to the 3/2 du. So I now have to integrate this. So that's going to be the opposite of the integral of 3 times. When I integrate u to the 1/2, I'm going to get 2/3 u to the 3/2 minus the integral of u to the 3/2 is going to be 2/5 u to the 5/2 plus c. Simplifying that, I get negative 2 u to the 3/2 power plus 2/5 u to the 5/2 power plus c. And again, remember that we have to go back to x. I'm going to replace all of the u's with 2 minus x. So I end up with negative 2 times 2 minus x to the 3/2 power plus 2/5 times 2 minus x to the 5/2 power plus c. Again, please pause the video. I just went through this pretty quick. Pause the video. Make sure you're comfortable with each and every step, what I did along the way. And if you're not sure about something, please, again, make a note of it and ask about it in class next time. Now let's take a look at another way of doing change of variables. And this is really with a definite integral. And this is going to be a pretty common one. Problems like this do appear on the AP exam, both in practice in just actually giving you a problem and just wanting you to integrate it, or like for response where they might be kind of a theory type thing. So what you have here is we got to change a variable. We're going to let if u equals g of x and it has a continuous derivative on the closed interval from a to b, and f is continuous on the range of g, then the integral from a to b of f of g of x times g prime of x dx is going to be, when I change the variable, I'm going to let u equal g of x, du is going to be g prime of x dx. It's going to be equal to g of a, the integral from g of a to g of b of f of u du. In other words, this is a complete change of variable, and we do adjust the limits of integration because we're going to let u equal g of x. So I need to know when x is a, where does u go? That's what g of a is going to be. When x is b, since u equals g of x, we know u is that upper limit is going to be g of b of f of u du. Let's take a look at a problem that uses this process. In this case, we have our example is we're going to take the integral from 0 to 2 of x over the square root of 1 plus 2x squared dx. Now I'm going to pull that x down in front. And so I'm going to let, in this case, I'm going to let u equal 1 plus 2x squared. So du is going to be 4x dx, and so I know dx, du over 4 is going to be x dx. So I have that. Now the other thing I have to do here is my lower limit. Since u is 1 plus 2x squared, I know that when x equals 0, I'm going to get 1 plus 2 times 0 squared, which is going to end up equaling 1. So when I do my whole change of variable, my lower limit of integration is now going to be 1. When the upper limit, for the upper limit, which is 2, I say u equals 1 plus 2x squared. I'll put 2 in for x, and I get that this upper limit is going to be 9. So when I make my change of variable here, this is going to be the integral from 1 to 9 of 1 over the square root of u times du over 4. I bring that 1/4 out, and I should still have the 1 to 9 in there. So it should be 1 and 9 of u to the negative 1/2 du. Taking that definite integral there, the antiderivative of u to the negative 1/2 is going to be 2u to the 1/2. So I have 1/4 now times 2u to the 1/2 going from 1 to 9. Plugging in the 9, I get 1/4 times that in brackets here, 2 times 9 to the 1/2 minus 2 times 1 to the 1/2. Well, 9 to the 1/2 is the square root of 9, which is 3. So I'm going to get 1/4 times 6 minus 2, which will be 1/4 times 4, which equals 1. So this definite integral right there is equal to 1. Again, pause the video. Look over every calculation I did here. Notice the process. Identified what u is. Okay, did du, all the stuff that we did before. But we added in one other thing. We had to determine what the new lower limit of integration is, what the new upper limit of integration is. So by doing that, I now have this definite integral right here, which is a little bit easier. It's easier to solve, and so I can go and do that because it fits a basic rule that I'm familiar with. So make sure you're comfortable with that. Again, if there are any questions, make sure you ask next time. Now let's take a look at a numerical integration technique, which is the trapezoid rule. The idea behind the trapezoid rule is that instead we can use it to approximate a definite integral, but instead of going through and using rectangles like we did with the Riemann sum, we use trapezoids. So when I work with that on the trapezoid, I will go through, like if I'm going to take the integral from 1 to 4 of x squared dx, my first trapezoid is going to have that as base, that as a base, and this part right here is going to run right up next to that curve. And we're going to run here, and then we'll get another one there. Now, so what I can do is I've got 3 trapezoids here, and I'm going to add those up. I'm going to find the area and add them up. I have this formula right here, that the area of a trapezoid is 1/2 delta x, which is the height, times base 1 plus base 2. So in this case, for our trapezoids, my first trapezoid, this one right there, it's the area, using the area formula, I'm going to get 1/2. The height is just the change in x, which is 1, times the sum of the two bases. Well, that's going to be, when I put 1 into x squared, I get 1. When I put 2 into x squared, I get 4. So my bases are 1 plus 4, and that comes out to be 5/2. Area 2 would be 1/2 times 1 plus 4 plus 9, which would be 13 over 2. And area 3 is going to be 1/2 times 1 plus times 9 plus 16, which gives me 25 over 2. So therefore, I can go through and I can approximate this. I can say the integral from 1 to 4 of x squared dx is approximately equal to 5 over 2 plus 13 over 2 plus 25 over 2, which would be equal to 43 over 2. Now, another thing I want you to notice here, because it's going to come into play in a second. We go through, notice on here that I'm using my function, each function value, but the function value at each end point. So in this case at 1 and 4, I just use one time. I use the 4 twice, I use the 9 twice. Okay, that will be a pattern that's going to be used as with this trapezoid rule. We're going to go through, the more trapezoids you have, the better approximation it is. But I want you to notice that it does give you a little bit better approximation than maybe the rectangles, because we get a smaller amount of error as we do that problem. Now let's take a look at this more in general. We can say that the integral, use the trapezoid rule, is really going to be this whole thing right here or here. And this piece right here, we're going to show you another way that we can go through and deal with this as well. The integral from a to b of f of x dx is going to be approximately b minus a over n over 2n, which is really 1/2 times delta x, of f of x0 plus 2 times f of x1 plus 2 times f of x2 plus dot 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 plus 2 times f of xn minus 1 plus 1 time f of xn. Now notice, remember on that what I said last time, when we did the integral from 1 to 4, the one at 1 and then the function value at 4 were used one time. All the ones in between were used twice. So this is right there, that's f of a, that's f of b. So we could think of it as 1/2 times delta x times this expression right there, which is the same as what we had up there. Okay, so what happens on this one, if you know, the one thing you do have to have a regular partition on here to use this version of it. You can go through and use the trapezoid rule, finding the area of each individual trapezoids and adding them up like we did on the previous one. Even if we could do that process, even if the partition had different widths, if it was not a regular one. But to use this form right here, we do have to have a regular partition. Now, what's going to happen on this? One option we have with this is we can work with a table of values. Remember, a function can be defined using an equation. It can be used with a graph. It could be used with a table. And so what I want to do on this one is I want to go through and use the trapezoid rule to go through and evaluate this one. Well, I could go through and write it out. I could go through on this one and say, you notice my delta x in this case is 0.25. So I could say 1/2 times 0.25 times 4.32 plus 2 times 4.36 plus 2 times 4.58 plus 2 times 5.79 plus blah, 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 2 times the 8.08 plus the 8.14. I could write all that out and add it up, do the multiplication, and get the answer. Another way we can do this on here is I can go through, and I'm going to add a couple columns here. The first one is going to be a factor. And the factor is either going to be 1 or 2. And in this case, it's 1 here, and it's 2 at all the other spots, except for the last one. Now, what I'm able to do at that point, I can go here, and I'm going to create the next column. And what I'm going to do is I'm going to multiply f of x times its factor. So I'm going to get a 4.32. 2 times 4.36 is going to be 8.72. And 2 times 4.58 is going to be 9.16. And 2 times the 5.79 is going to be 11.58. 2 times the 6.14 is going to be 12.28. And then 2 times 7.25 will be 14.50. 2 times the 7.64 is going to be 15.28. 2 times the 8.08 is going to be 16.16. And then I have the 8.14. Now, what I can do now is I can add that up. So I want you to pause the video right now and add those values up and get your total. Welcome back. When I did it, I came up with that this sum was 100.14. Hopefully I've done all these calculations. I did all these calculations up here correctly. And then I got the 100.14. So now what I know, that 100.14 is everything we have here. So I can say now that the integral, in this case, from 0 to 2 of f of x dx is going to equal 1/2 times 0.25 times the 100.14. I can now put that into my calculator. And when I do that, do those calculations, I get that the answer comes out to be about 12.518. So that's what I came up with when I did this one. Again, hopefully I didn't make any mistakes when I made these calculations right here, or when I added it up. So if I did make a mistake, please let me know. But if you should have gotten this, the 100.14, and then you get the 12.518 for the approximation of that definite integral using the trapezoid rule. With that, this does conclude this video. It might be a little bit longer. I know it's a lot longer slides than what I've given you in the past. But it does kind of cover a little bit with section 6 as well. With that, we will conclude chapter 4. And so next week we are getting ready for break, but we do have our test on chapter 4, and so that will be taken care of before the break, and then we'll get to the exam. We'll give you the exam on Friday. So I hope everything is going well, and I'll see you in the next class.